disparate group of values for defining relationships. They have 94,000 relationships that use them. And then morphology, another 66,000 substances and observables. So that's where the bulk of the SNOMED activity is when it comes to defining relationships. What I haven't mentioned in going through those two pie charts is really the special hierarchies. These are neither the source nor the value of a defining relationship. And so they can be linkage concepts, such as attributes or link assertions, or also special concepts. When we inactivate a concept, we put it into the inactive concept hierarchy. Concepts that are useful for navigation, we put into a navigational concept hierarchy. To identify namespaces, we have a namespace hierarchy. So, I'm talking about hierarchies. What are these hierarchies all about? Well, we're really talking about, from a computer science standpoint, a directed acyclic graph. And the graph is organized according to what we call subsumption relationships. There's a single root at the top, because the computer science tree is upside down. And then the various nodes are linked to each other by defining relationships that we call attributes, and those attributes have values. In description logic language, we call these existential restrictions, but it basically is an attribute value pair that defines the connection between two concepts or two codes. So the description logic definitions for each concept code are made up of structured combinations of ISAs and attribute value relationships. Well, let's take a look at a diagram that illustrates that. Here we have viral pneumonia, infectious pneumonia, pneumonia and infectious disease, and lung disease. So viral pneumonia is a kind of infectious pneumonia, and infectious pneumonia is a kind of pneumonia. Likewise, virus is a kind of infectious agent. So those are the ISA relationships, the subsumption relationships. And then if we look at the attribute value relationships, the existential restrictions, we have a relationship between A and B with a relationship. And this means that for every instance of the A, there is at least one relationship with a value that's an instance of B. So let's look at viral pneumonia. For every instance of viral pneumonia, there is at least one causative agent relationship to at least one instance of a virus. And likewise for infectious pneumonia, there is a causative agent relationship to the infectious agent code in the terminology. So if we put the ISA relationships, which are sort of vertical, and the attribute value relationships, which are horizontal with these curved arrows, we have a single graph that shows the relationships between all of these different concepts. And of course, if you take all 320,000 SNOMED concepts and almost 1 million relationships, it will form a huge graph that you can't put on a single sheet of paper, but it's all organized in this fashion. The way it's organized is according to the principles of what's called description logic. So let's say a little bit about what is description logic. From a mathematical standpoint, a description logic is a particular member of a family of logics. You might say, well, how can you have a family of logics? The point is that a logic is constructed by certain operators, and if you choose different operators, you get a different member of the family of logics. So this family of logics is characterized by a formal semantics, formal way of determining its meaning that's based on set theory. So we call that set theoretic semantics. It's also characterized by proofs of correctness and completeness of computation. So you can build algorithms that are guaranteed to find all and only the subsumed or the correct subtypes of a particular expression. And then the algorithms for doing that have proofs that tell us about their complexity, so that there are algorithms that, worst case, only require polynomial time, and others that are exponential, or so-called NP-complete, or exponential time, and so on. From a knowledge representation viewpoint, description logic is a set of constructs for representing terminological knowledge. Terminological knowledge is that which is always true of a meaning. So the terminological knowledge about a heart attack or a myocardial infarction is that there's a morphology of infarction, and it involves the myocardium, the muscle of the heart. Now, besides terminological knowledge, you can have assertional knowledge. Things like, well, MIs are usually associated with chest pain, and they often involve diaphoresis and fainting and arrhythmias and so on. But what's terminologically true about a myocardial infarction is just it's an infarction, it involves the myocardium, and that's it. So that's what we try to represent using description logic in SNOMED. And of course, we want to have algorithms and implementations of those algorithms so that we can test pairs of expressions to see whether one is the subtype of the other and vice versa, so that we can classify and structure a set of expressions according to their subsumption relationships. So here's an example. A headache is a kind of ache which has a finding site which is located in the head. So headache is marked as defined in the concepts table because that's a sufficient definition of what a headache means. So this means the class headache is sufficiently defined as the set of instances of the class ache which also have at least one finding site relationship to an instance of the class head structure. And all instances of the class ache that meet those criteria, that have a finding site head, are also instances of headache. Now you might say, well, is that really what I mean when I say headache? And we could debate about that. In other words, if somebody punched me in the nose and my nose hurts and my nose is part of my head, does that count as a headache? Well, if it does, then this is the right definition. If it doesn't, maybe we need to change the definition. But the logic helps us to explicitly and clearly express exactly what we mean logically by